Hello everyone. I'm from the University of Science and Technology of China. It's a great honor to be here to present our work. Our work focuses on correcting and mitigating shortcut learning behavior in deep neural networks. I will introduce our work from four aspects. First, let's begin with the introduction. As we all know, deep neural networks, despite their notable progress across information retrieval tasks, encounter the issues of shortcut learning and struggle with generalization due to their reliance on superior correlations between features and labels. For example, in image classification tasks, dogs are often identified by the context of their typical background settings, like grassland, which can lead to the mixed identification of dogs in less common settings, like the beach. Existing studies on mitigating shortcut learning in DNNs often adopt data augmentation and model distillation to solve this problem. However, it will take substantial labor and may introduce unintended biases. So in this paper, we find a noteworthy parallel between the shortcut learning behavior of DNNs and the students' knowledge learning in the educational settings. We find that for students, using a formula for arithmetic or geometric series summation can efficiently solve most similar math problems. However, performing poor when confronted with more intricate problems that the formula cannot directly solve. Similarly, DNNs learns a superior correlation between grassland and dog. It performs well on similar data, but struggles to recognize the dog of the same breed without the grassland backdrop. In this paper, we propose COMI to correct and mitigate shortcut learning behaviors in deep neural networks. This is the overall framework of COMI across NLP and CV tasks, mainly consisting of character, habit, and deep mitigation strategies to mitigate shortcut learning, and feature extractor and information separation modules to help DNN focus on underlying semantics. In the whole framework, we adopt BERT in NLP and ResNet 50 in CV as our feature extractor. First, empirical risk minimization models can rapidly use shortcuts to converge during the initial iteration of training. Our goal is to inhibit the model from learning these shortcuts in the early training process. So we propose correct habit to retrieve the top M challenging samples to learn, followed by solving the remaining samples in the dataset, which focus on complex information-rich samples, helping the model spot shortcuts less and more slowly. It's important to figure out whether difficult samples need to be redefined during the learning process of the model. So we evaluate four correction methods for the task of natural language inference with ERM, as shown in the figure. The first method, without correction, involves training with random sampling from the dataset without making any adjustments to the samples. Following this, we select the top M challenging samples based on the pre-trained ERM model, named the first correction method, sorting samples directly according to the pre-trained knowledge. In each training epoch, the model prioritizes learning from these top M challenging samples. We then invert this process in the inverse correction method. Besides, in each epoch, the top M challenging samples are redefined based on the training records of the previous epoch in the sustained correction. As seen from the result of the figure, the first correction method outperforms overall on both ID and OD samples. So the first correction method is adopted as the correct habit strategy. Then, to enhance the model's ability to extract underlying features, we design information separation module to separate the information into task-relevant information and task-irrelevant information, which could help the model concentrate on more efficient information. The task-relevant information fits the true distribution, and the task-irrelevant information conforms to a uniform distribution. After separation, the model gains the ability to focus on learning more task-relevant information for making predictions. However, there is a potential issues with some shortcuts present in task-relevant information. These shortcuts can help allow the model to quickly learn correlations between features and labels, but they may hinder the model from delving deeper into extracting the underlying information. Therefore, we can conclude two key points. First, overconfident predicted tokens may include genuinely correlated tokens for accurate predictions. Eliminating these tokens can undermine prediction performance. Second, eliminating certain shortcuts may lead to the emergence of the new ones. For instance, eliminating some stop words or comma words does not guarantee the absence of other stop or comma words in the data. To mitigate the shortcut learning behavior hidden under task-relevant information, we design shortcut margin nodes to help DNs rely less on superior correlations. Besides, for unknown shortcut issues in NLP, we first deploy Linan to pinpoint confident tokens that influence the model's behavior near the instance being predicted. Then we design shortcut margin nodes by reducing the feature weights of top K confident tokens within the sample, which not only ensures the retention of important tokens, but also prevents the emergence of other shortcut tokens. Based on the above process, we can reduce the influence of shortcuts in task-relevant information and make the final prediction on the truly relevant information. In the experiments to validate the performance of COMI on ID and OD samples, we perform extensive experiments on the full dataset of NLP and CV to fully evaluate the robustness of COMI. Each dataset has its own training ID and OD subsets. In this paper, we investigate 4 kinds of shortcuts: next call and overlap shortcuts in NLP, background and texture shortcuts in CV. The detailed statistics of the dataset are shown in the table. For NLP tasks, we perform comparative experiments with common baselines shown in the table on the MNLI and QQP compared to the backbone BERT. The comparative baseline typically achieves generalization enhancement at the expense of decreased accuracy of ID. However, COMI can improve OD generalization without reducing ID performance. In CV, we adopt general data augmentation and regularization method without prior knowledge of the shortcuts. Some methods that estimate the pseudo shortcut labels when ground truth labels are unvaluable. As shown in the table, our method outperforms all baselines, enhancing OD sample performance while maintaining excellent ID sample performance. In the evaluation study, it can be seen that different modules play different roles in different tasks. Besides, we conduct experiments on the ranking percentage M in the correct habit strategy. It can be seen that as M increases, the performance of the model in ID sets decreases. In NLP, the optimal settings of M can balance the performance on ID and OD sets in 5% to 50%. In CV, the optimal setting of M is in 50% to 20%. To dictate post-separation embeddings, we employ TXNE realization performed on the ImageNet 9 dataset. Notably, predictive task-relevant and task-irrelevant representations exhibit distinct forms and spatial distributions. Among them, the task-relevant information naturally segregates into 9 clusters in the embedding space, reflecting the 9 classifications. To better compare the model confidence on ID and OD samples, we adopt expected calibration error ECE scores for evaluation. No ECE scores in the hands subset demonstrate that COMI learns underlying features rather than spurious correlations in the data. Finally, we make some salience analysis on NLP and CV tasks. For NLP tasks, we show 2 cases where integrated gradient explanation presented in the figure. Obviously, in the first case, the 2 sentences are non-duplicated, but there are lexical overlap biases. The pre-trained BERT captures certain shared tokens, like a bank account, and some inconsequential symbols. In contrast, COMI concentrates more on crucial tokens, while ignoring simple shortcuts. For CV task, we adopt GradCam to present salience in maps of some images to evaluate the performance on mitigating the shortcuts of background and texture. We can see that the COMI performs adaptively by accurately detecting real objects. In this paper, we can conclude 4 points. First, drawing inspiration from the way students used to overcome shortcuts in educational scenarios, we aimed to encourage the model to reduce reliance on shortcuts and extract more underlying features. Second, we proposed a correct habit strategy to retrieve the top and challenging samples with the highest losses for priority training. Then we constructed a deep mitigation network with a shortcut margin loss to mitigate potential shortcuts hidden within task-relevant information. Finally, we conducted extensive experiments on natural language inference, understanding, and image classification tasks, where results demonstrated the effectiveness of our proposed COMI. So this is all the introduction of our paper. Thank you all.